This problem we're going to calculate the equilibrium constants for ethanol dehydration for the case where water is a gas phase product and the case where water is a liquid phase product. And we're going to calculate the equilibrium constants from the exponential of minus delta G of the reaction standard conditions over RT, and likewise for K2. So let's look at delta G reaction for the first reaction, and that's going to be delta G formation of water as a gas plus delta G of formation of ethylene minus delta G of formation of ethanol as a gas. So these are values, because we're at 298 K, we can just directly look up in a table. So I'm going to pause and look these values up in the table. So this is delta G for the first reaction. Now delta G for the second reaction, the only difference is this first term is minus 237.21 for a liquid, and then the other terms are the same. So let me pause and calculate them. Well, since the delta G's are different, when I calculate the equilibrium constants, they're also going to be different. The equilibrium constant is, of course, delta G formation, first reaction over RT. So I'll again pause and substitute the numbers in. So I've calculated the equilibrium constant for the first reaction, and do the same calculation for the second reaction using, of course, delta G for the second reaction. So these values are different, so let's look at why they're different. So I can write the equilibrium constant for the first reaction in terms of fugacity of water at equilibrium, divided by pure component fugacity of water as a gas at 1 bar pressure, ideal gas, and likewise fugacity of ethylene divided by pure component fugacity gas, also 1 bar pressure. And here we have fugacity ethanol at equilibrium divided by pure component fugacity ethanol at 1 bar pressure. Pure component ideal gas, 1 bar pressure, fugacity is the pressure, and so that means this becomes fugacity of water over 1 bar, fugacity of ethylene also divided by 1 bar, and then the fugacity of ethanol divided by 1 bar. And we typically just write this as fugacities with the understanding this equation is only correct if we use units of bar for fugacities. Well, I can do the same thing for K2, and let me pause and write that down. So the thing that's different is, of course, the fugacity of water is the same at equilibrium, but the standard state now is water as a liquid, and that fugacity then is going to be the saturation pressure. So we rewrite this, fugacity of water divided by the saturation pressure, water at 298, fugacity ethylene, and then the fugacity of ethanol. So you can see this is fugacity of water, fugacity H4, and the saturation pressure water. So these two equilibrium calculations differ by the saturation pressure water. So we look at this equation, K2, this term is just this term, which is K1. So K1 divided by saturation pressure water is going to be equal to K2. So let's see if that indeed is the case. We calculated K1 0.0348. From the steam tables, the saturation pressure in units of bar, so this ratio 1.11, that's K2. Indeed, that's the same value of K2 we calculated up here from delta G value. So what this shows is when we change delta G values, we change the fugacity standard states. Even though we have different equilibrium constants, we have the same equilibrium composition.